Welcome back. And so in the last lecture, I will talk about spectral sparsifiers via sketching. But I think I do have a few minutes to just give you a brief idea of how these L0 samplers, that is, the sketches that allow you to sample a random coordinate from the support of a vector, are constructed. So let me do that and then go to the content of lecture 4. Okay, so L0 samplers. Let me remind you what these are. So basically, an L0 sampler is this linear sketch that takes an n-dimensional vector, compresses it to a few dimensions, and most of the time, except for a low probability error event, lets you output a uniformly random coordinate from the support of the vector. Okay. Good. So in fact, this is a special case of a somewhat more general primitive, and this more general primitive is known as the LP sampling problem, or LP samplers. So let me tell you what these are. So think of really, you have a database, you're given a stream of data items, and again, you're making a single pass over the stream. And then at the end of the day, what you want is a primitive that will sample, so to speak, a representative element out of your data set. And if you want an LP sampler, then if fi is the number of occurrences of your item I, then you want to output I with probability proportional to fi to the p, naturally normalized by the pth norm to the p. Okay. I will not talk about LP samplers. I'll just give you an idea of how the L0 samplers are constructed, which we used. And the idea is fairly simple. Basically, so what do we want? We want to construct this linear sketch that will allow us to recover a uniformly random coordinate of x. And the simplest possible setting is this. Well, suppose that our x is actually one sparse. So x has just one non-zero coordinate. Question is, can I design a simple sketch that will allow me to recover this coordinate? And I will show you such a sketch in a minute. And well, if we solve this case, then we can solve the general case, because if our x is t-sparse for some t, so if the support size is t, then what we can do is just subsample the universe of data items independently at rate about 1 over t. This is basically what we did for the distinct elements problem. And the subsampling of our x, which was t-sparse at rate 1 over t, will often be 1 sparse. So we can solve the problem using the first sketch. Okay, so here's the question then. Suppose that my signal x, I have a vector x in Rn, and I'm promised that there's exactly one non-zero in this vector. Can somebody suggest a sketch? So I want a matrix S, and I want the matrix actually with just 2 rows. I'm claiming that you can design a matrix with simply 2 rows, such that if I have S times x, then I can recover x exactly. Can somebody tell me how to do this? So I have a vector x, it's 1 sparse. There's exactly 1 non-zero coordinate somewhere, and I don't know what the value is. I'm claiming that I can design two vectors, so my sketching dimension will be 2, such that if I have the dot product of x with these 2 vectors, I can recover the identity of the coordinate and the value. How can I recover the value, for example? What should I dot with?
1, 1, 1.
1, 1, 1, 1, 1. Good. So suppose I have the value. How can I recover the coordinate?
1, 2, 3, 4.
Thank you. Okay, good. So this is the sketch. All right. The first row will be just 1, 1, 1, 1, 1. The second row will be 1, 2, 3, 4 through n. So if my vector x has 1 non-zero, so it's some alpha times the I starth coordinate vector, then the dot product of the first row with x is just alpha. The dot product of the second row is alpha times I star. So I can figure out alpha and I can figure out I star. Okay, good. So this means that if x is 1 sparse, then I can recover x. So what if x is not 1 sparse? Well, suppose we don't really know the sparsity of x, but suppose we do for a second. So let 2 to the j be the closest power of 2 to the sparsity of x, to the number of non-zeros. Well, select a subset, S, subset of coordinates, by including every element with probability 2 to the minus j. So in expectation, the intersection of the support of x with this s is 1. And a calculation shows that it's pretty likely that the intersection will actually be 1. And furthermore, if the intersection is 1, it's a uniformly random 1 in the support of S by symmetry of the distribution of S. Good. And that's basically how L0 samplers are constructed. This is the main idea. To get the tight parameters, one needs to massage this a little bit. But basically, this is what we do. We will try log n powers of 2 to guess the sparsity. And we'll run one sparse recovery on the subsampled version of our signal. Well, at least one of them will succeed with high probability. There are some issues because this sketch from the previous slide that we defined, it works well if x is actually one sparse, but if you run it on an x that has more than one coordinate, it will just give you some garbage, and you won't even know that this happened. But this is fixable because you can check, you can store one other sketching row that just lets you check whether or not your recovery was successful. This is because you can test if a vector is 0 with high probability. Okay, good. And this is really how L0 samplers are constructed. It's just a subsampling of the universe plus a couple of rows to recover one sparse vectors. And so note that the interesting part is that now if we are in a dynamic stream, namely if since I have a linear sketch, so if the intermediate data stream contains a lot of items and then they are deleted, the sketch still works. This is because only the final x needs to be one sparse. Okay, any questions on L0 samplers? All right. Okay, so in that case, let's move on to more powerful primitives for approximating graphs, for compressing graphs and preserving some interesting information about them. So I will talk about spectral sparsification in dynamic streams. And naturally, the motivation is that we have huge networks today and we want to compress them and preserve certain properties. So for example, community structure. If you want to preserve community structure, then you do want to preserve cuts, or you want to preserve properties of random walks and various questions of this type. Good. So let me first define what sparsification is. And this talk will be, this lecture will be a little bit more high level, because this also deals with fairly new results, and I won't have time to properly go into all the details of sparsification primitives. Okay, so what is sparsification? Suppose we're given a graph G. It's an undirected graph, and there are n vertices and there are m edges. Think of m as being very large. Here's G on the left. What we want to do is find a smaller subgraph G prime, and usually it will be a subgraph of G prime, but the edges will be reweighted. There will be weights on edges. And we want G prime to approximate G in some form. So for example, here's G. G has quite a few edges. G prime on the right has fewer edges because, sort of, for instance, we took this part and we replaced the number of edges with one thick edge. So our G prime will normally be a weighted graph. So think of taking a bunch of edges, sampling a few of them, and including them with high weights. Okay, so for example, what we will be interested in is graphs G prime that approximate G in the following sense. That if you look at any cut in the graph G, and if you count the number of edges that cross the cut in the graph G, so in this case the cut is this red line, and the two edges cross the cut, and then you look at G prime, you look at the exact same cut, sum up the weights of the edges that cross the cut, the numbers that you should be getting should be multiplicatively close. 1 plus minus epsilon, epsilon is some precision parameter, think of 0.01 or so. Okay, good. So this is what this will be about. But let me tell you about a specific type of sparsification, which is spectral sparsification. And for that, it is useful to start with the notion of sparsifiers that ensure that we approximate cuts in the graph G. And what I want to do is express cuts in the graph G in terms of this edge incidence matrix. This is something that we have already done for the spanning tree application, but I want to do this again and look at it in a more general framework. So suppose that this is our cut. So this is the graph G, and I have this red cut. What I can do is I can write down the value of this cut as the sum over all edges of the in E of the difference of xu minus xv squared. where x is the indicator of the cut. So x has zeros on one side and ones on the other side. So if an edge does not cross the cut, then xu minus xv is 0. If it does, it's either 1 or minus 1, but we're squaring things, so it doesn't matter. Okay, good. So in particular, this means that the value of the cut is the L2 squared norm of this vector z. And this is a vector z of dimension n choose 2. Remember that we had the edge incidence matrix B. And the vector z is basically the vector of differences, xu minus xv, over all the edges in the graph. And this vector of z is also known as b times x, the edge incidence, times the indicator of the cut, which is something that we have seen before. So the value of a cut is the L2 norm squared of bx, where x is the indicator. Okay, good. So as in the previous lecture, we will heavily use this edge incidence matrix. And so let me remind you that each row corresponds to a potential edge. So there are n choose 2 rows. So here's an edge uv that is actually in the graph. So this is a 1 and a minus 1, and everything else is 0. If something is a non-edge, then it is identically 0. Good. Good. Okay, so what we have is that the value of a cut given by x, and x is the indicator vector, is nothing but x transpose b transpose x, because this was the L2 norm squared of bx. And b transpose b is exactly the Laplacian of g. So what this means is that the quadratic form of the Laplacian, that is x transpose lx for various x in Rn, in particular encodes all the cut information in the graph. So if you plug in values of x that are 0, 1, you just recover all the cut information. But this is more general, because you can look at the quadratic form of the Laplacian evaluated at arbitrary x on the real line. Okay, so this brings us to the following definition. This is from Karger from '96. We say that a graph G prime is an epsilon cut sparsifier of a graph G if the following holds. So L is the Laplacian of G, B transpose B, and L prime is the Laplacian of G prime, B prime transpose B prime. So G prime is an epsilon cut sparsifier if all cuts in G prime approximate all cuts in G up to 1 plus minus epsilon multiplicative error. This can be phrased in terms of the quadratic form of the Laplacian as x transpose L prime x is sandwiched between 1 minus epsilon x transpose Lx and 1 plus epsilon x transpose Lx. And this should hold for all cuts. This is the same as ensuring this condition for all x in 0, 1 to the v. Okay. And in 96 and in 94, this is a result by Karger, and of 96 by Benzer and Karger, it was shown that any graph G with any number of edges admits an epsilon cut sparsifier with order 1 over epsilon squared and log n edges.
Does it have anything to do with the Johnson-Wiesenstrass lemma, or is it just a coincidence?
Yeah, I see. I wouldn't say that there is such a direct connection. You mean, where does the 1 over epsilon squared come from?
Yeah, 1 over epsilon.
It's just from basic probabilistic statements, right? It's sort of, if you want something to be correct up to 1 plus minus epsilon, then there's variance, and you need, yeah. Good, and it's known how to construct such cut sparsifiers in linear time in the size of the original graph. So you can compress a graph G with an arbitrarily large number of edges, up to n squared, of course, down to almost n log n. Sort of just a few spanning trees, basically, with weights. Okay, so this is to preserve cuts. On the other hand, we will deal with a more general notion of sparsifiers. We'll say that G prime is an epsilon spectral sparsifier of G if the quadratic form of the Laplacian of G prime is sandwiched between 1 minus epsilon G, 1 minus epsilon L and 1 plus epsilon L in the positive semi-definite sense. This is the same as saying that we'll have this constraint, but not for all x in 0, 1 to the v, but that is all cuts, but for all x in R to the v. So think of assigning arbitrary real values to vertices. Okay.
What was the difference again between this definition and the previous one? Just
The difference is which set of X do I want this to hold? So I'm looking at two quadratic forms, L and L prime, and I'm evaluating them on a set of vectors R, set of vectors X. In the first case, I just want to ensure that all cuts are approximated. So I evaluate them only on 0, 1 vectors, right? And this is what it means to be a cut sparsifier. Here, I'm saying, let me compare the quadratic forms. I'll require something much stronger. I'll compare the quadratic forms on all real, to be close on all real X multiplicatively. And in particular, this can also be written in a more compact form using the positive semi-definite ordering. So L prime should be dominated by 1 plus epsilon times L in the PSD sense, meaning that 1 plus epsilon L minus L prime is positive semi-definite. Same things here, and on the other side. Yeah. Okay. So a result from Spielman and Teng, and then from Spielman and Srivastava in 2009, shows that any graph G admits an epsilon spectral sparsifier with also about n log n edges. So you can compress any graph with up to n squared edges down to 1 over epsilon squared n log n with weights. And you can construct such sparsifiers fast. So note that this is an extremely powerful notion, and there has been a lot of work on this. In particular, the fact that these are spectral sparsifiers, so being a spectral sparsifier is a very strong statement. One can see, for example, that if you look at the eigenvalues of G prime and the eigenvalues of G, all eigenvalues will be multiplicatively close. And also, random walks in G will behave similarly to random walks in G prime in certain senses. So a spectral sparsifier really preserves a lot about the graph G. And this has applications for numerical linear algebra, combinatorial optimization, and other questions. Okay, good. So these sparsifiers exist, but how do we construct spectral sparsifiers? The way to do it is, one way of doing this, is using a theorem of Spielman and Srivastava that says the following. Given a graph G, we will form G prime by looking at every edge E of G and including this edge in G prime with probability PE, which is related to the effective resistance of this edge. So this is a measure of importance. So basically, this is an importance sampling scheme. We look at the edges of G, we compute some measure of importance for every edge, and we'll ensure that, and then we sample every edge with probability proportional to its importance, so to speak. So now the right measure of importance ends up being the effective resistance of an edge in G. What is the effective resistance of an edge in G? You think of the graph G as a network of unit resistors. You think of injecting 1 unit of current at one endpoint and taking it out at the other endpoint. The effective resistance is the potential difference that is induced. And we'll see some useful characterizations later. So RE is the effective resistance. Good, so we sample edges, and if we take an edge, then we give it weight 1 over the sampling probability, so that at least in expectation, our graph is preserved. So the expectation of G prime is G. So Spielman and Srivastava in 2009 showed that with high probability over the sampling process, L prime will be sandwiched in the PSD sense, in the positive semi-definite sense, between 1 minus epsilon L and 1 plus epsilon L. So the upshot is that we need to sample edges according to some measure of importance and then upweight them with inverse sampling probability to make the estimator unbiased. Okay, good. So let me just give you a small example to show what this measure of importance is trying to do. And this is a fairly natural example. So indeed, it does make sense that for some graphs, we need to include certain edges with pretty high probability, and for other graphs, many edges should be dispensable. For instance, if this is our graph G that we saw in the previous lecture, then say there are these 2 edges that cross the cut. And so, of course, if I want to construct a graph G prime that at the very least approximates the cuts, I had better keep these edges pretty much with probability 1. Because this is a cut that is crossed by few edges. So the measure of importance on these edges will be high. On the other hand, if I have a graph G prime, if I have a graph G that looks like a complete graph, then I should be able to sample edges with rather uniform probability because they're all the same after all. Okay, good. So this is a high-level overview of the algorithm of Spielmann and Srivastava. So now what we would like to do is to show how to construct spectral approximations to graphs in the streaming model of computation. So now think of this graph as being huge, and the edges of the graph are given to us, just as in the previous lecture. We have small space, and we would like to construct a spectral approximation at the end of the day. Good. So the good news is that by the results of Spielmann and Srivastava, we know that at least these approximations exist that we can store in n polylog n space. As we know that there exists a spectral sparsifier that only has n log n edges, if epsilon is constant. So this is our model. So suppose that now edges of the graph G arrive in an arbitrary order in the stream. We are given access to n polylog n space, and we want to take a single pass over the graph and output a spectral sparsifier at the end of the day. Good. Well, the first question to ask is, we have this black box algorithm of Spielmann and Srivastava that takes a graph, loads the graph into memory, and in time proportional to pretty much the number of edges in the graph, if you discount polylogs, gives a spectral approximation with few edges. Can you do this in the streaming model of computation? Well, it turns out that if we have an insertion-only stream, it is very easy to take this offline algorithm and turn it into a streaming algorithm. It's very similar to the example of spanning trees that we saw before. Basically, because it's an insertion-only stream, as edges come in, we were just adding them to some spanning tree. And as soon as an edge comes in and connects, both endpoints belong to the same component, we know that we'll never need this edge anyway. So something very similar happens if you try to design streaming algorithms for sparsifiers in insertion-only streams. Why is that? Well, this is because, in a way, we want to sample edges with probability proportional to some kind of measure of importance. But as I add edges, other edges become only less important. So I don't need much memory. Good. And it was shown in two papers by Anguche in 2009 for sparsifiers, for cut sparsifiers, and by Kellner and Levin in 2011 for spectral sparsifiers, that basically these algorithms are streamable. Just as the edges are coming in, just keep resparsifying this in some tree-like fashion, and you'll get the right result. And so now we want to understand, okay, so suppose that the edges are both coming in and disappearing. Can we design dynamic streaming algorithms for graph sparsification? And again, the same example applies. So suppose that this is our graph G, and at some point in the stream, we get this graph, and there are two edges that are crossing the cut. Any spectral sparsifier would have to include these edges. Pretty high probability. So they are important. On the other hand, at some point, I can give you more edges that cross the same cut. These two red edges now look completely unimportant, but everything could be deleted, and we're back to square one. So the question is, what should we store about the graph to extract spectral information? We can't store subsets of edges. And this is the point at which the results that we saw in lectures 1 and 2 come together to get an algorithm for spectral sparsification. Because remember, in lectures 1 and 2, we were designing two types of algorithms. Well, first, we're interested in the following. Given a vector x as a stream of updates, design a linear sketch that will let you approximate the L2 squared norm of x. And there's a good reason why L2 squared norms should matter. Because recall, what we're interested in is a spectral sparsifier, so we want two quadratic forms to match up. So in general, remember the value of a cut in G was the L2 squared norm of b times x. So this is the reason why we want L2 squared norms for this result. And we will also use the heavy hitters algorithm that we developed in a second. Good. So the classical data stream applications that we have seen solve the following question. We have this vector x that is being updated in the stream, and we want to approximate, say, the L2 squared norm using space much smaller than the dimensionality of the vector. Something that we have seen in the second lecture is the AMS sketch. The AMS sketch was just storing the dot products, was maintaining dot products of x with 1 over epsilon squared random plus minus 1 vectors. You can also use Gaussians. It's the same thing. Good. And so we got a 1 plus minus epsilon approximation in order 1 over epsilon log n space. Good. And this was a linear sketch because we're storing dot products. Good. Good, good. 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 So now we will design a graph sketch that is useful for sparsifiers. And the way we will do it is, indeed, we will sketch the edge incidence matrix of the graph and then reconstruct the edges of a spectral sparsifier. Let me just tell you a little bit, and this is the theorem that we will get. This is a theorem that we proved in 14. We will get a single-pass dynamic streaming algorithm that uses only O tilde n polylog n space up to epsilon factors and allows us to reconstruct a spectral sparsifier at the end of the day in polynomial time. So we will get updates to the edge set of a graph G in a stream. Think of the graph G as being undirected. We will compress the graph down to n polylog n space and unpack a spectral sparsifier in some polynomial time. So this is pretty good in terms of space. So first, there's a single-pass dynamic streaming algorithm. So this is all very good. The space is optimal, up to polylog factors. One very exciting open problem that still hasn't been solved yet is to reduce the polynomial. Ideally, we would like to have a streaming algorithm that reconstructs the object that we're interested in time proportional to the size of this object. So recall, for instance, for heavy hitters, we were maintaining always the top k elements roughly at cost k. We have to look at the entire stream, but sort of it was efficient. When I'm asked what are the top k coefficients so far, I could give them to you very fast in time proportional to k. And so here, the runtime is actually n squared, at least, and n squared polylog n, which is suboptimal. So ideally, there's definitely an algorithm, probably an algorithm with runtime n polylog n. Okay, so there's some work on this before. So for instance, in 2012, Anguch and McGregor and us also had an algorithm for cut sparsifiers. So this is only the ones that preserve the quadratic form of the Laplacian for 0, 1 vectors x. But this turns out to be easier than this question. And there are some partial results on spectral sparsifiers using linear sketching, but none of them could match the optimal space bound and and also do this in a single pass. So note, this is quite surprising. This is an oblivious compression scheme. So you take a graph, which is roughly an n squared dimensional object, you compress it without even looking at the graph, because we generate the sketch from some fixed distribution. And then from there, you can reconstruct eigenvalues approximately. It's quite nice. Okay. So let me tell you now how the algorithm works. And the algorithm works as follows. So for that, we first need to look at the theorem of Spielmann and Srivastava a little bit more and understand how this measure of importance works, the effective resistance of edges, if you view the graph as an electrical network. Good. Any questions so far? Okay. So Spielmann and Srivastava show this. If one way to construct spectral sparsifiers is to look at our graph G, we sort of load it into memory, then we go to every edge, and we perform this experiment. We route one unit of flow, inject it into one endpoint, take it out at the other, compute the potential difference. This gives us the effective resistances. So R sub E is the effective resistance of edge E in the graph. Then we form the vector of sampling probabilities, PE, by letting PE be the min of 1 and the effective resistance times a large constant log n over epsilon squared. So it turns, yeah. And then we sample each edge independently with probability PE. If the edge is sampled, we'll give it weight 1 over PE. All right, good. So one observation in particular is, so we will show how to basically implement this algorithm in the streaming model using sketches. So one thing to note, so we'll not look at the entire algorithm because it takes more time. We will look at some main ideas. So one thing to note is that if I have an edge E of high effective resistance, and high here means, say, at least 1 over log n, then the probability of sampling this edge is exactly 1. I just take all the edges of high effective resistance. So this is very similar to this statement that I made before, that if I have a graph, and the graph consists of two parts that are loosely connected, maybe there are 2 edges connecting the 2 components, then I have to take both edges pretty much. But there are more interesting examples where edges don't actually, an edge can have high effective resistance without crossing a small cut. It will not quite go there. Good. Okay, so this is our plan. What we would like to do is mimic the algorithm of Spielmann and Srivastava. But we want to do this using linear sketches, which means that we want to design a matrix S such that, similarly to the connectivity algorithm, if we maintain S times B, where B is the edge incidence matrix of the graph, so remember for connectivity, S was just this L0 sampling sketch. Then, from S times B, we need to be able to do 2 things. So first, from this compression of the graph, so if it seems that we have to compute sampling probabilities, PE, for each edge in the graph, which is pretty crazy because we don't even know which edges are in the graph. At this point, we compress the graph to n polylog n size representation, but we don't know which edges are in. And once we somehow manage to compute these PEs, then we are supposed to sample edges independently with probability PE and upweight them 1 over PE, which also seems a little bit crazy because, again, we don't know which edges are in the graph. And this is supposed to be doable from a sketch. Okay, good. So we need to learn somehow, so the upshot is that somehow we need to learn how to sample using a sketch. So the way out is, of course, to note that, we don't necessarily have to compute these sampling probabilities for every edge in the graph. All we need to learn is somehow to set up a sampling process that only learns about those edges that have high effective resistance and only learns about a sample of the edges with low effective resistance. So for instance, if I have a complete graph, I don't really need to know which edges are in. I need to know about a sample. Good. Good. So we want to design this sketch S that allows us to sample edges of G according to effective resistance from the sketch. And this is a non-trivial problem. So to solve this problem, we'll give us a hint. So let's introduce a simpler problem. And the simpler problem will be the following. So suppose that I'm given a sketch of the edge incidence matrix of the graph, but together with a sketch, I'm also given a pretty bad spectral sparsifier of G. So I have my graph G, and I want to construct a 1 plus minus epsilon approximation G prime to G. Now suppose for a second that I'm given not a 1 plus epsilon approximation to G, because then I'd be done, but suppose that I'm given as a hint a factor 100 approximation to G. So I'm given a graph G tilde, and I'm given it explicitly. This is a graph with n polylog n edges. I'm able to store it completely. This is something that I will do at the decoding step. So this is this G tilde. So G tilde satisfies a much weaker guarantee. I want the Laplacian of G tilde to be at most the Laplacian of L, but at least the Laplacian of L by, say, 100. And I will show that if I'm given this help, if I'm given the G tilde, then I can design a sketch S, such that with both of these pieces, I'm able to get from a crude constant factor spectral approximation G tilde and some more information about the graph in the form of a sketch, I will get to a 1 plus minus epsilon sparsifier G prime. I will boost a bad constant factor approximation to a good 1 plus minus epsilon approximation. Any questions about the plan? Yes?
There's just one thing that I didn't get. The resistance of the edges.
Mhm.
How are you estimating that? Because you need to know how the graph looks like to get this value, right?
Yes. So the question was, how will we use effective resistances? This will be the next slide. Yeah. So for now, the statement is that I want to get a very good approximation to G from a sketch, but I can't quite do this in one shot. So I'll do a sequence of refinement steps. I'll assume that I have a reasonable approximation, factor 100, and I will convert this into a factor 1 plus minus epsilon. So technically, I need to learn how to sample edges according to effective resistances. Let me simplify the problem even further. And I'll simplify it by saying, okay, remember, we have to take all the edges that have effective resistance at least 1 over log n. Let's just learn how to do that. So here's my new problem. I will want to design a sketch S such that if I'm given S times B, the edge, the matrix of the graph, and a crude constant factor explicit sparsifier G tilde, just a set of n polylog n edges with weights, then at the very least I can figure out which edges in G itself were edges of high effective resistance. Let's do that. And that's not enough, because I know that I need to take all of these edges with probability 1. I will also need to sample others, but once we know how to do this, it will be believable that we can do the rest. Okay, and so now is the point at which we have to figure out what is it. So what is this property of effective resistances that we will use? Okay, so what is the effective, suppose we have a graph G, so here it is, and let's look at an edge, or maybe at a non-edge as well. Let's look at a pair of vertices, U and V. So these are the blue and the red vertices. Now the effective resistance between U and V, and it's not only defined for edges, it's defined for vertices as well. We can talk about the effective resistance between U and V. So the effective resistance between U and V is the following quantity. This is one expression for it, is BUV transpose L plus BUV. Okay, so this takes a little bit of time to parse. So L is the Laplacian of the graph. L plus is the pseudo-inverse of the Laplacian. BUV is the corresponding row of the edge incidence matrix. It's just minus 1 at U and plus 1 at V. This particular expression will not be that important, really, but here's what we will use. So what is the effective resistance? It is the potential difference that arises on the vertices of the graph if you inject 1 unit of current at U and take 1 unit of current at V. So here's the experiment. I inject 1 unit of current at the blue node, I think, and take it out at the red node, or the other way around. Then one can see that by linear algebra, the set of vertex potentials that arises from this experiment is exactly the pseudo-inverse of the Laplacian times this BUV vector. This BUV vector just has a minus 1 at U and a plus 1 at V. That's exactly what it's saying. Inject 1 current at U, 1 unit at U, take it out at V. And if you look at Kirchhoff's law and Ohm's law, you will realize that the set of vertex potentials that arises is exactly L plus. Is exactly L plus times L inverse times BUV. Okay. Good. So now this is not quite, and in fact this already explains this formula, but it's not that important. So what is important is that these vertex potentials induce an electrical flow in the graph. And the flow on an edge xy, this flow is shown here, the flow on an edge xy is exactly the difference between the potentials of y and x. Good. Good. So in particular, that's why the effective resistance between U and V is the potential difference induced when you send 1 unit from U to V. So a more interesting characterization of the effective resistance is the following. We let F be the vector of currents on the edges of the graph. So as I just said, the current on an edge from x to y is just the difference in potentials. So the vector of currents is actually B, the edge incidence matrix of our graph, times the vector of potentials. This is a true statement. Okay, and now comes the characterization of effective resistance that allows us to use the heavy hitters primitives to recover the edges of the graph. Because the effective resistance of an edge E turns out to be the fraction of the L2 squared mass, the fraction of energy of the electrical flow that arises when you inject one unit of current at U and take out 1 unit of current at V, that is carried by the edge E. So here's what it means for an edge E to be a high effective resistance edge. So suppose that I'm interested in these two vertices, the blue vertex and the red vertex. And I inject 1 unit of flow here, I take it out there, and these orange edges are the edges of the flow. And an edge is thick if a lot of flow goes over that edge. So this edge is extremely thick, and this means that the effective resistance of the edge UV is very high. Now, formally, the effective resistance of the edge E is exactly the squared value of the flow that goes over that edge, divided by the sum of squares of flow values over all the edges in the graph. And this is exactly the characterization that we need. That is, edges E in the graph that have high effective resistance are heavy in L2 squared sense. If you know the right set of vertex potentials phi that correspond to routing 1 unit of electrical flow from U to V, then if you look at the matrix B times phi, then the fraction of the L2 mass, a lot of L2 mass of the corresponding vector, B times phi, will be contributed by your edge. Okay, any questions on this?
So in general, any cut edge will have, on a min cut, if an edge falls on a min cut.
Ah, great, I see. So if the edge, so say, okay, if the min cut is 1, then the flow will just go along that cut. If you have a small min cut, then the edges of the min cut will carry a non-trivial amount of flow. Yeah, good point.
Are
So,
these guys being estimated exactly, or just?
Okay, good. So this is a thought experiment at the moment. This is a very optimistic thought experiment saying, oh, sort of suppose that somebody gives us, I want to design a tester. Something like, is my edge UV present in the graph? And I want to understand how can I even get to that? How can I even design a sketch that will let me test if an edge UV is present in the graph and has high effective resistance? So I do know a primitive I do know count sketch that shows that if my edge is heavy in L2 squared sense, we have this heavy hitters algorithm, then I can figure out that the edges, I can figure out the identity of that edge. So I'm trying to massage the spectral specification problem into something that looks like classical streaming techniques are applicable. And this is the characterization. Yeah, so there are lots of issues yet, because nobody really gives me the vector of potentials phi. It's a big mystery. Okay, good. So this is what I would like to do. I would like to design a tester of the following type. I'm given a crude sparsifier G tilde of G, and I'm given a sketch S times B of G. I'll get to design this sketch. And I'm also given a pair U comma V. What I want to know is, I want to answer the following question. Well, is it true that the edge UV is in the graph G, and it's a high effective resistance edge? So, yeah. So for instance, if the edge UV is in the graph, but it has low effective resistance, I don't have to know it. I don't have to be able to figure that out. So I want to be able to know, is it true that the edge is in G and is a high effective resistance edge? Here's how I will solve the problem. So by the discussion that we just had, the following is a characterization of high effective resistance edges. Now, suppose that I'm given this edge UV, and I would like to do the following. I would like to say, okay, let me compute the set of vertex potentials phi. I can't really do it, because to do that, I need to know the graph G, but suppose for a second. If I compute the vector of vertex potentials phi, then I can compute also the flow values by taking the matrix B and multiplying it by phi on the right. Of course, I can't really do that because I don't know the matrix B, but we'll figure that out. Once I do that, I look at the vector of flow values, well, here it is, and I just check, I just check how much of the L2, how big of a fraction of L2 squared mass is contributed by coordinate E. So for this example, when UV is this blue node and this red node, the edge is in the graph and it's a high effective resistance edge. So by this characterization, my vector F, the vector of flow values, looks something like this. There are some zeros, because some edges are not even in the graph. Other edges carry a small amount of flow, so that they have small flow values, small values on them. But then there's this edge E that I was corresponding to UV is in the graph and has huge effective resistance, so I see something really big there. And now this actually starts looking like the L2 heavy hitters problem, because remember in count sketch we had this huge vector of dimension n, and we wanted to figure out which elements were heavy in L2 squared sense. Like for example, if we had this situation where all the elements are 0, 1, and one element is root n, then we were able to figure out the identity of that element. And this is where we're going. Okay, good. So this is when the edge is actually in the graph. Well, if for a pair UV, the edge is actually not in the graph, then so this is this pair UV, and we just have a 0 there. So it does look like, if we can distinguish between the two cases. Good. So now, of course, there are these problems. Namely, we don't have access to the matrix L, neither do we have access to the matrix B. Let's solve these problems one after another. Well, I will not give the details here, but it turns out that if I don't have the matrix L, it's okay. Remember, I made the assumption that besides the sketch, I'm also given this crude spectral sparsifier G tilde. It turns out that I can compute the vector of vertex potentials using G tilde. So there's this G that I don't know, and there's G tilde that approximates G spectrally, not very well, but spectrally, so it's a strong statement. What I can do is I can imagine computing the vertex potentials corresponding to the electrical flow from U to V in G tilde. And I can use these vertex potentials on G. It turns out that if G tilde was a factor C approximation factor C spectral approximation to G, then this characterization still holds. If our edge E was a high effective resistance edge in G, like at least 1 over log n, then if I knew the right set of vertex potentials, then I would have omega of 1 over log n on the right-hand side. Okay, if my G tilde is a factor C approximation to G, I'll lose something. My edge is not quite as heavy. It doesn't contribute as large of a fraction, but it's only 1 over C. So this will go into our space complexity. So this is not too bad. Okay. Good. So this is a fix for the first problem. How do we compute the set of vertex potentials? We still have another problem, namely to compute the vector of potential differences. So we no longer call it a flow vector because it was a flow vector in G tilde. It's just a set of potential differences over the flow, the graph edges in G. Let's call it delta. Well, we can't compute this vector delta because we don't know the matrix B. Okay, this is exactly where L2 heavy hitters come into play. Because remember, what do we need to do? We have this huge vector delta of dimension n choose 2, and we have one coordinate in hand. We want to understand, is it true that this one coordinate contributes a 1 over log n or so fraction of entire L2 squared mass? We don't have to know the entire vector to figure that out. This is what we did in the count sketch lecture. So L2 heavy hitters, which is something that we have seen, not quite in this form, but pretty much. If you look at what we showed in the lecture, this is exactly it. Okay. So suppose that I have a vector y of reals, and look at one coordinate I in this vector. We say that this coordinate is a L2 heavy hitter with parameter eta if the square of this coordinate is at least an eta fraction of the entire L2 squared mass. Basically, in the first couple of lectures, we showed that for any parameter eta, there exists a randomized linear sketch in dimension about 1 over eta log n that will let us reconstruct all the eta heavy hitters. How does that work? Well, remember we were repeating something log n times and we were hashing into B buckets. Well, you would need to hash into 1 over eta buckets. And the same analysis we'll go through. Okay, good. Any questions, concerns? I think I'm running a little bit out of time, but not so much. Good. So what this means is that we can compress a very long vector, and we will run this L2 heavy hitter sketch on the vector of n choose 2 dimension. We'll compress it down to dimension about log n. Why? Because we have this eta parameter, but remember the eta parameter for this particular application was 1 over log n. So all in all, our dimensionality will be polylogarithmic. And very efficiently, we'll be able to figure out which coordinates are heavy. Good. 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 Yeah. So now what this means is that, okay, we have this vector delta, and we need to test whether or not a given edge, which is an element of this vector, is heavy in L2 squared sense. Fine, we don't have to look at the entire vector. We could sketch it. Now, of course, we can't really sketch the delta, because as in the connectivity application, the particular vector delta that will arise depends on the execution path of our decoding algorithm. So what we need is a sketch. So basically, instead of sketching delta, what we'll do is we'll just store a sketch of the matrix B. Because remember, delta was just B times the vector of potentials. So by linearity, it suffices to apply the sketch to the vector B. And then once we actually know which vector of potentials we need to test on, we just combine the sketched version. We look at S times B multiplied by phi, and we're fine. And run the L2 heavy hitter sketch on that. Okay, good. So now this is what the algorithm looks like. We take an L2 heavy hitter sketch, and we maintain S times B under dynamic updates. And just to convince you that this is n poly log n space, well, the heavy hitters algorithm compresses n choose 2 dimensional vectors into poly log n dimensional vectors. This is the same as sketching the columns of the edge incidence matrix. So every vertex basically stores a polylogarithmic number of bits. Okay, good. So this is what we got. This is what we got. Given a sketch S times B of G and a crude sparsified G tilde and a pair UV, we can figure out whether or not U and V is an edge in G of resistance 1 over log n by doing the following. For this edge, we'll compute the vector of vertex potentials, and then we'll recombine columns of the sketched version of B using this vector of vertex potentials, and check if the eth coordinate of the vector actually contributes a lot of L2 squared mass using the L2 heavy hitter sketch. Fine, this is good. So this lets us solve this basic problem. That is, at the very least, recover all the edges in G that have high effective resistance. So we knew that those had to be taken with probability 1. Let me just say a few words about what else we need to do. Remember, if an edge has low effective resistance, say effective resistance R, then we don't have to necessarily include it. We have to include that edge with probability 2 to the minus j. Now it seems tricky to learn about these edges because if you redo this analysis, you will see that such edges only contribute a 2 to the minus j fraction of L2 squared mass. So you can't really reconstruct all of them, but that makes sense. Good. So this is hard, but the point is that what we can do is we can just sample. This is a trick that we have been using all along. We subsample the universe of edges. So think of subsampling the graph and sketching the subsampled version. So if we have an edge that has effective resistance 2 to the minus j, then one can show that if you sample the edges of the graph G at rate 2 to the minus j, then if this edge survives, the corresponding, it will contribute a 1 over about log n fraction of L2 squared mass. So basically we sample proactively, and those edges that had to be sampled at this rate will contribute the right amount of mass, and we will be able to recover them. Okay, Good. So now this is the algorithm, modulo one bit. So this is an algorithm that we call refined sparsifier. Takes several parameters. So the graph G, it takes the graph G in a sketched form, then the graph G tilde, which is an explicit crude sparsifier, a parameter epsilon, which is the precision that we want, and a parameter C, which is the precision of the crude sparsifier. What does this algorithm do? Well, this algorithm just does brute force search over all the edges. It tests for each pair AB in V choose 2. We will run this procedure that we just discussed to figure out if the edge is in the graph. To be more precise, for each edge AB, we first compute, using this crude sparsifier, the right sampling rate, which is the effective resistance of this edge in the graph G tilde. I'm skipping some details there, but this is the main gist. Then we look at the right sampling level. Remember that we stored sketched versions of the subsampled matrix B. We look at the right sampling level, and using the L2 heavy hitter sketch, we test whether or not this edge was in the graph. And so if the edge E, AB, was sampled, then we know it contributes a high amount of L2 squared mass, so this tester will say yes, and will include the edge. It will repeat this many, many times and take the edge. Okay. So this solves this problem. That is, remember we started with the following question. We are given a crude spectral sparsifier G tilde of G, and we want to design a sketch S times B such that from these two pieces of information we can refine a sparsifier, namely go from G tilde, which was a bad constant factor approximation, to a 1 plus minus epsilon approximation. But this was assuming that somebody gives us G tilde, and that's tricky because nobody does. How do we get out of this? Well, we resolve this issue by using a very nice approach from a result of Miller and Peng that basically says the following. Imagine, so let's not think about sparsifying the graph G itself, but let's think about a sequence of graphs G. We introduce another parameter lambda, and we let G lambda be the graph G plus a copy of the complete graph pasted on top of it. In the actual algorithm, it's a little bit different, but this is the gist. So it's the graph G plus the copy of the complete graph pasted on top of it, but the edges of the complete graph have weight lambda. So if lambda is 0, then that's just G itself. But if lambda gets higher and higher and higher, this starts resembling the complete graph. So basically, this fine structure of the graph G is slowly obliterated as we increase lambda. And well, think of these graphs for a sequence of values of lambda. If lambda is very small, say 1 over poly n for some large poly, like 1 over n squared or 1 over n cubed or so will suffice, then the graph G lambda is pretty much G. And you can show that it approximates the graph G well, spectrally. On the other hand, at the other extreme, if we look at G of 1, it's the graph G plus a complete graph. And for that graph, G of 1, just the complete graph itself is a really good spectral approximation. And this is the point. So now what we get is we consider values of lambda that correspond to powers of 2, from 1 over poly n all the way to 1. So there's only a logarithmic sequence of graphs to consider. One can also show, and sort of this is a chain of graphs. One endpoint of the chain looks very much like G, the graph that we want to sparsify. The other endpoint of the chain is a very simple graph. It's a graph that's approximated well by the complete graph. So it will serve as our crude sparsifier. Furthermore, two adjacent graphs in this chain are similar, because if you decrease lambda by a factor of 2, it is not hard to see that two adjacent graphs basically sandwich each other spectrally up to a factor of 2. And this is what we will do. Remember, we have this procedure that is called refined sparsifier. And this procedure had to take a sketched version of some graph, and it needed a hint, which was this crude sparsifier that we assumed. But now we can do it, because the first thing we'll do is we'll look at the graph G1/2. We'll sparsify that using a sketch and the complete graph, because the complete graph is a good approximation. We will get a really good approximation of G tilde 1/2 using our result. Then we will use G tilde 1/2 as a crude sparsifier to get a good approximation to G tilde 1/4. We'll use G tilde 1/4 to get a good approximation to G tilde 1/8. And in a logarithmic number of levels, we'll be down to G tilde of 1 over poly n, which is exactly a good approximation to our graph G. Okay, good. So a quick summary. So the space is polylogarithmic, because basically there is a chain of logarithmic length, there's a logarithmic number of various sampling levels, and we used a heavy hitter sketch of polylogarithmic size. Note again that, as in the connectivity algorithm, we crucially used these, so to speak, composable sketches. We sketched the matrix B, and then in the algorithm we actually needed a sketch of B times some kind of vector of potentials. So in connectivity, this was just B times the indicator of a cut, and here this is a B times the vector of potentials. So even though the decoding process is highly adaptive, and it runs in a logarithmic number of adaptive steps, the sketch itself is non-adaptive. All right, good. So and that's just a quick summary of the 4 lectures. So we started with very basic statistical primitives, such as the AMS sketch, that is approximating L2 squared norm. Heavy hitters, count sketch, L0 samplers, and so these are the primitives that take as input a long vector x. Rather, they take it as a sequence of updates, and they use a linear sketch, and allow us to solve some basic problems. Now, we used these primitives to solve graph connectivity and graph sparsification. So for connectivity, we took the edge incidence matrix and applied L0 samplers to it, because connectivity is sort of an L0 type problem. What matters is cuts that are crossed by a small number of edges. Graph sparsification and spectral sparsification in particular is more of an L2 type problem, because we're looking at the quadratic form of the Laplacian. So the right tools were the heavy hitters and the AMS sketch, because inside this primitive we had to figure out, does a certain edge in the graph contribute a large fraction of L2 squared mass. And there are lots of open problems. One of them I mentioned already. So can you get a linear time sketch for graph sparsifiers? So reduce our runtime from n squared to n, or n polylog n. And what about other problems? You want, for example, the shortest path metric of the graph. Is it possible to design an oblivious sketch that compresses the graph down to some small amount of space and approximates all shortest path distances? That would be very exciting. Or can one prove that this is not possible? Okay, thank you.